Hi there, Nick here, M0NTV, and welcome back to the Shack. And finally, I've been looking forward to this one, the unveiling of the brand new homebrew 17 metre SSB rig, which I've been building for what feels like forever. But in truth, it's probably about a year. And the reason it's taken me so long to build this one is because I keep stopping and making YouTube videos about it. But it does mean that if you've been watching these videos for the past year, you'll have seen a lot of this radio come together, the different modules that we've built and tested and, moved on to the next bit. So, without any further ado, I'm very proud to introduce you to
the SHELF-17. Oh yeah. There it is. And this is a 17 metre SSB transceiver, putting out 83 watts peak envelope power, built on a wooden shelf. And we'll get to why I took that particular design decision in a moment. But let me just show you the thing in all its glory first of all. So I'm going to try and not waft the camera around too much, but let you see it. So if we start over here, what we've got here, so you can see the microphone amplifier coming in there, and over here obviously we've got the speaker and the audio amp and preamp. Some of these modules will be familiar to you if you've been following some of the videos over the past year. Now behind the speaker, which I can get a very good view of this is one of the mixers. This is the mixer modulator on its end there, and on top of that is actually the tuning tone oscillator. Produces the 1 kilohertz tuning tone, so that's over there. This is the steerable IF stack on its side. Down at the front here, I didn't do any video on this. This is a design I've used a few times before. This is the Doug D'Amore S meter for radios that don't have any kind of AGC to tap off. So it's just an audio-derived S meter, and I doubt it has much accuracy, especially my version. As you can see, I've reused this old meter that has normal and high, so it's just got a dancing needle, and I think the needle's pegged as well. It has. Yes, that's when you don't have an AGC, you see. Right, okay, so that's just a little speed, but I like to see the needle dancing around in the middle, so that just taps off the audio input to the audio preamp. Now, round the front here, you'll probably recognise this. This is the kind of brains of the operation, really, I suppose. So that is the Arduino Uno in that little stripy tin with the LCD screen and the rotary encoder on the right for tuning. There's the transmit LED at the top there, and there's various connections that come out of there, as well as the two coaxial leads, which are the VFO and the BFO. Right behind it, tucked in here, is another mixer, the second mixer. Down here, I didn't do a video on this one, but this is the switching, and I'll perhaps say a word about that in a minute, and the various switching that goes on, which this time I've actually controlled by the Arduino, so I could put a bit of a delay in between switching certain things off and other things on. So I thought I'd give that a bash this time. And what else? Coming forward over to here, now this little stack here, these are the transmit amps. We've got the bandpass filter on the bottom there in that little metal tin, and then the stages of the transmit amps, finishing with what was going to be the pre-driver but ended up being the driver on top, and then that feeds onto the monster that is the PA, with a high power bandpass filter on the side, and because that needs 50 volts, I had to get a beefy boost converter here that will supply that with quite a few amps as well, to give that what it needs. Round the back, you can just about see, this is just this is like the final switching that takes place before we kind of leave on this bit of coax here, and goes into the SWR power meter. And I'm not actually using the tuner because the antenna that I've got is resonant. So in a moment, I'll play some video of me tuning around and stuff, but I've got it switched on. Just a bit of band noise really at the minute, but in a minute we'll hear some footage when conditions are a little bit better, and you can actually hear some signals and hear what it sounds like, and do some various tests and things. In terms of the other switches that you can see, so the actual PTT is here, and over here, these two switches. This bottom one controls the tuning tone on or off. So down means you've got the tuning tone engaged, and up means it's off. And this top one really controls the power level. What it's actually doing is turning the bias on or off to the PA. So if the switch is up, the bias is on. If the switch is down, the bias is off, and that just means that you can cut the power, particularly if you're tuning up. As I said, tuning's not really an issue with this particular rig at this time, just because I've got a resonant antenna on the band, so that's really helpful. But I thought I'd build that in. Yeah, so that is it, and we'll have a little think and a little play with it and test it in just a minute. But first of all, I thought perhaps better say why I chose to build it kind of al fresco, open plan, all like this on a bit of wood. So why did I build it on a wooden shelf? Well, three reasons really. First of all, there is a curse that befalls many home brewers, which is you build this radio and it takes you a while, and you lay it all out on the bench. And I do this with every radio I've built, and you've got it all connected up, and you have to tweak it and sort it out, and fault find any problems, and you get it working, right? So you get the whole radio spread out on the bench, and it works. And I've had radios like this. I've been making contacts on this radio that's spread out on the bench. But then the minute you take it apart and put it into its permanent home, some tiny metal chassis, or in my case, not so tiny, usually. But the minute you get it in the enclosure, of course, it doesn't work then. So you've got to do the whole thing again and work out, and it could be a myriad of different reasons. You broke a connection off, or something's grounded or touching something else, or two modules that played very nicely together when they were further apart are now closer together and don't, all kinds of different things. I kind of thought, wouldn't it be great if I didn't have to put it in an enclosure? Wouldn't it be good if I could just leave it, Well, unless you've got the space just to devote a whole workbench to this radio project, which I haven't, few of us have, then that's not really an option. But this was the next best thing, to put it out in the open, as it were. You've got to be careful, of course, because the I know what some people are saying, shielding, yeah, and that is an issue, and I have to be
honest, I've had to be a bit creative. There is some shielding, localized shielding on it, and I had to think carefully about where I placed some of these things. The biggest bugbear with this, of course, is because it's producing some power. Obviously, you've got RF flying everywhere, and to be honest, I really should have just enclosed that PA. I think that would probably have helped things. But anyway, that being said, it works. It works fine, and that's fine. And lots of people have built on bits of wood. Bill Mira, N2CQR. It talks about Frank Jones, who used to regularly do this. Bill himself has built radios on pieces of wood. In fact, he built a whole chassis around, a wooden chassis around this one that he did recently. Charlie Morris, ZL2 CTM, often builds his radios on big sheets of wood. He'll screw the modules down onto them, and sometimes he'll break them up and put them in an enclosure, and sometimes he won't. So I'm in good company. There's lots of people have done this. Secondly, it's a bit of a joke really, because if you listen to the Solder Smoke podcast, and you should do if you're into home brewing, where Bill and Pete, N6QW, are talking about all things home brewing, and there's a standing joke about the Shelf of Shame, which is this place where you put your radio projects that don't work. And sometimes, they can languish on the Shelf of Shame for a few weeks. Sometimes it can be a lot longer, And Pete confessed the other day that he's actually got a whole room of shame. But as he's been building radios for a lot longer than I have, I think he's probably earned the right to have that. But I kind of thought, well, if this has got to go on the Shelf of Shame and it doesn't work, at least it comes with its own shelf. Right. But thirdly and finally, I've spent a lot of time and effort on this over the past year, and when you finally got a radio together on all these different modules and bits, and it works, and it seems kind of sad, really, that you take all this hard work and then you just put it in a metal box and never look at it again, and I just like looking at it. Is the truth, and in a strange way, it's kind of where art meets science, I think, and I like seeing it. I like looking and seeing all these parts, and because it reminds me of the work that was involved in doing it. So anyway, getting a bit deep now, aren't we? Let's move on. So what I want to do is just very quickly give you just a quick look at. Well, it's not a schematic because I don't do individual schematics. I do individual schematics for the different parts, but I don't do a whole schematic. It would be a nightmare. But it's a block diagram, so you can see. And just a very brief word about the switching, because I tackled that a bit differently this time. Then I'll show you some of the testing that I did about the transmit testing. And then we'll see some actual on-air footage of receive and a little bit on transmit. So hope you enjoy. I know it looks horrendous, doesn't it? Try and ignore all the red, green and blue bits at the moment. We'll get to those in a minute. But essentially, the layout of the rig is a fairly conventional superhet, really. So if we think about receive, first of all, we start on the left-hand side here with the antenna. So we go straight into an RF preamp, then into a bandpass filter, into the first mixer, which is being fed by an Arduino, which is powering an SI5351, an Arduino Uno, and that's controlling the VFO and the BFO, the beat frequency oscillator as well, the carrier insertion oscillator. So from the mixer, we're going through into the IF stack. Now I haven't drawn this right because, as you'll remember probably, it's a steerable IF stack. So essentially it's one-way traffic through the stack, and so all I'm doing really is just switching the inputs and outputs. But I drew it like this just because it's it's less confusing. And the IF stack, if you haven't seen the video on that, is essentially a crystal filter sandwich. So you've got a narrow band sideband filter, crystal cone filter, eighth order in the middle, and then on either side you've got just a simple IF amplifier. And then that feeds into the product detector, and that feeds into the audio amplifier and the loudspeaker. But also I'm tapping off, I haven't actually put it on this diagram because it was the last thing to include in the rig, but I'm also tapping off on the input to the audio amp to the Doug D'Amore S meter as well. So that's receive. On transmit, it's pretty much the same in reverse. So we go from the microphone through to the mic amp. That's being switched because I've got the little audio tuning tone oscillator putting out a 1 kilohertz sine wave, and so by controlling this tuning switch here, you're controlling whether we're feeding the mic into the modulator as it now is, or the audio tuning tone. But anyway, so it feeds into the balance modulator, back through the stack, and in actual fact, of course, it's actually going round to here and going all the way through the stack, and then back out to the second mixer now, the transmit mixer as it is, through the bandpass filter, through this little relay, which is actually attached to the RF preamp board. It's not actually going, obviously, to the RF preamp, but that's where the relay is. And then through into the transmit drivers, the small signal one, the driver, and the PA. And actually, I'm feeding it 50 volts. I began by feeding it 40, but I upped it to 50. Through the low pass filter, I think I called it a band pass filter in one of the videos, but it's actually a low pass filter. And then through to the final switching relay and to the antenna. And now what I decided to have a go at this time was inspired by a video I saw by another fellow home brewer, Paul Taylor, VK3HN, I believe is his call sign, who does some amazing rigs. And one of the things that impressed me, and I just hadn't really thought about it really, but he did his switching triggered by the Arduino, and because he did it in code, he could allow for a slight delay between switching things on and off. And I thought, what a useful thing, because what it means is you can control how fast things switch on and off. So essentially what this means, and I'd got that board with 4 relays on it, and it's only that I've had it knocking around the shack for ages, so I thought I might just as well use it. You could easily just do the same with separate little relays. And the Art Flash relays, they're just those cheap Songle relays, which are probably not the best in the world. They do handle a bit of power, which is good, but they're not proper RF relays or anything, but they work, and they're readily available, and they don't cost very much money, so that's why I use them. So I had that board, so I'm only using 3 of the 4, and actually, so the first relay is actually switching all the signal paths onto transmit. So when that relay triggers, it's opening up all the paths for transmit and closing them for receive. And on the other side of that relay are the receive bits and pieces that need to be, which is the blue stuff that need to only be on receive, like the RF preamp and the audio amps. And now the advantage of this is then, because the second one is power on transmit. So this is providing power to those modules that only need power when we're in transmit. So the microphone amp, the small signal transmit amp, and the driver. And finally, the third one is a separate relay just to switch on the bias of the PA. Now, the advantage with this is it means by switching all the signal paths first, it means I can make sure that all the signal paths are where I want them to be before I start pumping power through them. Because you could have a situation, particularly with this relay here, which is got some 83 watts, coming through from the transmit section. Now, if that relay doesn't open and close quickly enough, you could have a situation where some of that power makes its way through into the receive chain into the RF preamp and whatever, which is really going to spoil your day. So what it means is by doing it with in software, it means that actually I can just put a few, and it's only a few, a milliseconds delay, but it just means I can make sure these relays switch first, then I'll turn on the kind of lower power transmit stuff, then finally I turn on the P8. And as I said, because we're dealing in milliseconds, you don't notice it when you're operating it, but it's for a microcontroller. It's a difference. So yeah, so actually the PTT is software controlled. All the PTT does is just ground a pin on the Arduino, and then that tells the Arduino that we're in transmit. And then there's some control lines that come from 3 separate pins on the Arduino that then will go out to the board. And I will show you now what I actually did then. It's very, very simple arrangement with the actual switching. So here's how I did the actual switching. And this is an LT Spice simulation of what I did. This voltage source, imagine this is the relay, because how the relay works is it has a voltage on its pin, and each pin is exactly the same, so we're just using one here for demonstration. So it's got a voltage of 2.95 volts on it. Now that relay will switch when you ground that. So when that 2.95 volts goes to ground on that pin, it will switch. So that's what we've got to do. We've got to ground it. Well, how do we do that? Well, very simply, we just use a very simple transistor switch. So, and I'm sure you're fully aware how a transistor works. I won't go into all the details, but essentially, a very small current on the base results in a much larger current between the collector and the emitter. Note the emitter's grounded. So all we need is enough current just to open this transistor up to get beyond that 700 millivolts diode drop, as it is really, which is the threshold we need to reach to turn that transistor on, and then current will flow and we'll ground it, and the relay will switch. Now, coming from the control pin of the Arduino, I measured the voltage at 5.46 volts, so that's what's coming off the Arduino. So I took that right down because we do not want to load the Arduino, so we want to try and get that current as low as possible, really. So it sees a high impedance, and we're not going to load the Arduino down. But it needs to be high enough so that the transistor will turn on, and we can ground the emitter and get the relay going. That's the 5.46 volts on that. By the time it's gone through the resistor, that drops it down. You see, so we're just opening up. That's just going to be enough to get some current flowing, a little bit of base current flowing, which will result in current flowing here, and indeed will give us 57.3 milliamps, which should be plenty. Also, it's not going to tax the transistor too much by dissipating too much heat or anything like that. Very simple, but works well. And all I did is do this 3 times on each of the pins. And so when the code triggers this particular pin to go high, logic high, which is 5.46, that will do the rest, and we'll switch this relay on. Right, so we're going to do some testing on transmit to try and measure the transmit power and to have a look at the signal that I'm actually transmitting. So just to show you how I'm going to do that, we've got the rig on, and hopefully you'll see we're down there at 18.111 megahertz, and over here, this is the output here going out from the rig, coming around here. Ignore the tuner underneath, we're not using that. We're going straight into this little power SWR meter, and then out down to this tin here, and this is my homebrew, of course, dummy load. You'll see here I've got one of those high power resistors on there. Now it's supposed to be rated at 250 watts. I'm not going to put anything like that. I'm being a bit more conservative. I think I'm rating it at 150 watts. And so you can see it's got a big heatsink, not as big as the one on the PA, but a heatsink nevertheless. And I've got a fan here
if I need it down here at the bottom. But what's interesting about this is not only does it allow me to sync far more substantial amounts of RF, but you'll see here this little coil, this little inductor on the toroid. And what this is a current transformer as opposed to a voltage transformer. And what it's doing, it's tapping off the RF. So I'm able to get just a tiny amount of the RF power which is going through here. And actually, if I come around the side here, you can see, yeah, minus 30 dB. Now, in actual fact, it's about 32 dB's attenuation that I'm getting. Now, the great thing about that is that I can key down full power, sync lots of RF into here, but then I can also directly couple it then via that BNC to my expensive RF test gear that I don't want to put lots of watts through basically and blow up, and get a better idea about what the signal looks like and how powerful it is. So, and what that's doing is, so that BNC then is going round here, it's just skew round here, and that's going to come down here to the oscilloscope. So in a moment, what I'm going to do is I'm going to just press, this is the PTT, so press the PTT, this is the power switch, so up is full power, bias to the PA, down is no bias, so that's limited power, and this is the tuning tone. So I'm going to key the tuning tone, leave it at full power, and press the PTT, and so then we will inject a sine wave directly into the modulator, an audio sine wave about 1 kilohertz, and then we can check it on the oscilloscope, and then we do some calculations. Okay, well, I'm all set. I've got the audio tone switched on, I'm on full power, and I'm just going to flick the PTT. There we are. Well, yeah, 4.08 or whatever, 4.12, fluctuating a bit, just over 4. And if I just move this around over to here, so you can see the meter, and just repeat that same exercise. Yeah, you'll see, look at that, just over 80 watts there. And okay, well, let's do the calculations.
So I did a little calibration spreadsheet when I built the dummy load, and how I did this, essentially what I did is I used my commercial transceiver. I've got a Yaesu FT991A, thinking that probably the power levels are going to probably be reasonably accurate. So I stepped it up from 5 watts, which is the lowest it goes, and going up then, I didn't do every value, but up to 100 watts, and measuring the peak-to-peak voltage as I've just demonstrated, and then working out then what the attenuation is, and it's fairly stable. It averages out at 32.64 dB, but it varies a little bit, and I thought it might be helpful just to try and make it a bit more accurate. If you'd got a value of peak-to-peak voltage that you could kind of, even if you didn't have it exact, you could kind of go in between these two and you know, look at a calibration value that's a bit kind of closer to it, so you can get a more accurate attenuation. Yeah, so we can do that. So now, actually, it's easy life here for our purposes, because our actual peak-to-peak voltage I measured, and it's measuring 80 watts. Usually I get a little bit more out of that. It's interesting. It's usually about 4.2 something, but yeah, it's interesting. But anyway, but today, for our purposes, yeah, we measured 4.12. peak to peak, and so it's a simple calculation. You halve that to get the peak voltage. You then multiply it by 0.7071 to get the RMS, the root mean square voltage. You then square that, and then finally you divide it by your load, in our case 50 ohms. So that gives you your calculated power, which is 42.44 milliwatts. That's what we're recording on the oscilloscope. But of course, the actual real value is far, far higher than that, because we're attenuating it by 32.75 dB. So it's going to be, well over 1,000 times higher than that. So all you do then is you multiply that by that, and that's what it comes out to. You get 80 watts. So it's a simple enough thing. I had a bit of fun really playing around with this, and just to see how stable the attenuation was over the different power levels that I tried putting in. So yeah, I had some fun playing around with that. I'm not going to say any more about this now, and I can do something separate on this if folks are interested in this particular thing. Now, when it comes to testing the transmit audio, what I actually sound like on the rig, what I've done is I've done some very short station test recordings at some web SDRs around the world. I think one was in Norway, and one was certainly at a station in Fuerteventura in the Canary Islands. And conditions were not brilliant, to be honest, but it gives you at least some idea about how the rig actually sounds if you were to work me upon it.
QRZ Echo Uniform 1 Kilo Yankee. Okay, Charlie Tango 1 Echo Queen Oscar. Good evening. Echo United 1 Kilo Yankee. You're 5 and 7, 57 in the heavy static noise from the west. Name is Yuri. Yankee Uniform Romeo Yankee. How do you copy? Over. Okay, Carlos, you are 5'9" at the moment. Antenna is looking at you, and you are solid 59. Thank you very much for contact. 73 City 1 Echo Queen Oscar, Echo United 1 Kilo Yankee. Bye-bye. Sorry, Whiskey Charlie Delta. What is your prefix? Over. Okay. Okay, I copy. My apologies. Whiskey number 4, Whiskey Charlie Delta. Hello, good afternoon. Thanks a lot for coming. Apologies for the problems. The conditions are very poor, but I copy. The name is Justin. My name is Justin from Pescara, Italia. Over. Okay, thank you for the report. You are 5 to 6. We have worked before, and I'm very pleased talking with you again. The name is Justin, Pescara, Italia. Over. Tango, Italy, 2 Charlie, Charlie. Alpha, 6 Tango. Okay, Alpha, 3 Tango. Good afternoon, Nick. Are you 5 and 9? Over. Okay, great. Great, Nick. I'm going to confirm with you by lock of the world. 73, thank you. Bye-bye. Your modulation is very, very clear. No problem to copy you in Brazil. QSL? Bye-bye, 73, and good luck. QRZ, Papa Victor 8 Alpha Lima QRZ. Whiskey Papa 4, please make your call. QSL, Puerto Rico Island. Repeat again your call. Okay, Whiskey Papa 4 India. Good afternoon, my friend. Nice to copy you. You are 5 and 9 in Boa Vista, Brazil. My name is Hélio. Você é Colima de Ayahuasca aqui, yourself? Seven it is, and good luck and have a nice time. And thanks for 20 over 9. Good luck. Cure that. Papa Victor 8 Alpha Lima, cure that.
November Tango Victor, station test, testing, 17 meters. Station test, Mike 0, November Tango Victor, station test, opening Mike 0, November Tango Victor, station test, station test, Mike 0, November Tango Victor, station test, opening.
So there it is, the Shelf-17. And I have to say, since I've had it on the air, I've had some great contacts. Morocco, Algeria, Brazil a couple of times. So yeah, unfortunately, the band has not really been that open recently since I built the rig. But when it is, it's going to be great. So I hope maybe I'll be able to work you one day. That would be fantastic. So thank you ever so much for watching. And sorry this has been a bit of a long one, but quite a lot of stuff to get into. And I really appreciate all the comments and feedback that I get. I don't know what the next project's going to be. I'm probably just going to take a bit of time out and enjoy using this rig for a bit. But it won't be long before I'm firing up the Soldier 9 again. So to find out what I'll be doing next, stay tuned. And until the next time, thanks ever so much. Cheers. Bye-bye.